studied engineering for his undergraduate and master science degree, and then completed a PhD on applied mathematics at the University of Oxford. He's currently full professor in digital health and data science at the University of Edinburgh. And he'll talk about how data and mathematics transform our daily lives, from capitalizing on new technologies to managing healthcare challenges. Bueno, en español necesitan, bueno, no traduzco porque la charla va a ser en inglés, así que. Thank you, Thanasis, and you are very welcome.
Great. Thank you for the invite, and apologies that I don't know any Spanish. It's in my to-do list. At some point, I'll pick up the language as well. I have to admit, I feel like a fraud talking in front of distinguished mathematicians, and I was attending Daniel's talk, having all these equations. My talk is a bit more light. I come from a more engineering, applied mathematics background, and that is going to be reflected in my talk. So I think with this audience, it would not take me a lot of effort to basically convince you about who the best player of the world in football and who the best football team is. I've been a big fan of Albi Celeste for many years, and Lionel Messi, of course. But it might take me a bit of more effort to convince you about the need to be thinking in terms of simplifying concepts and not trying to overcomplicate mathematical equations. In the next 45 minutes or 50 minutes or so, I'll try to argue about, try to think in terms of Occam's razor, which suggests we should try to make models as simple as possible, but still useful, and not so much of what we call the Occam's professor, which basically indicates that we should try to overcomplicate things just to impress our colleagues and other colleagues in academia that we're doing something very convoluted and very smart. So I have split my talk into three thematic areas. And my idea is I'm going to give you something which hopefully resonates with each one of you. And the three thematic areas are quite different. So if you feel that one of the areas is not of your interest or not your cup of tea, you can kind of skip it, close your ears for the next 15 minutes, and then hopefully the next thematic area will be of interest. So the first thematic area I want to talk to you about is about the use of processing actigraphy data. Essentially, this is three-dimensional acceleration signals that you get from smartwatches and smartphones. And unfortunately, I'm not there, but I would take a good educated guess that the vast majority of you have one of those smart devices in your pocket. So if I'm right, probably the vast majority of you have smart phones in your pockets. And probably many of you have also smartwatches or this kind of wearable sensors. Now, again, it's probably something that I think we kind of take it for granted that this is a booming market, but just to put some figures for us to understand what we're talking about here, particularly people who are in the later stages, so beyond 55, at least in the UK, more than 70% of those people own a smartphone. And I don't have the figures for Argentina specifically, but it is increasingly becoming more and more affordable to own a smartphone. Not the latest, I'm not talking about the latest iPhone, but a smartphone, and some of the older smartphones are now recycled. And the vast majority of the population nowadays does own a smartphone. I think the latest figures are there are about 5 billion smartphones currently in use. And similarly, we live in the era that wearables are taking everything by storm. And just to give you an idea, in the next 3 years, this is projected to be a $70 billion market. So practically that means that in the not too distant future, probably the vast majority of us will have a smartwatch that we'll wear and they will use. In fact, I'm wearing two myself, and I'm not doing this for a show off in the talk. I've been doing this for the last 5 years or so. I've been using two wearable devices as part of my research. Now, with big data comes a big responsibility. And I want to start with a data set that I've been provided with, that basically we have the actigraphy data, so three-dimensional acceleration data, from 148 participants that we monitored for 24 hours. And the cool thing here is that we have data from wearable cameras. So for every single minute, in fact, every 20, 30 seconds, we know exactly what these people were doing. So that means we have the ground truth to understand if someone was sleeping, if someone was engaging in some jogging activity, some house cleaning, any kind of activity that you might think of on our daily lives. And that is particularly important because we can actually associate the kind of data we have been collecting from different kind of accelerometers, in this case from a smartwatch, but we can extrapolate this to data we get from smartphones as well, and map it onto the different kind of physical activity that someone might engage in. Long story short, this is the largest database I'm aware of that we have labeled actigraphy. So we have almost 160,000 minutes of actigraphy, which is labeled. So this from about 148 participants. And that's a quite remarkable data to be working on. Now, the raw data, if you see what your smartwatch or your smartphone collects, is something like that. So it's this XYZ that you might observe. So you have it over a period of time. So in this case, you have it over 24 hours on the x-axis. And basically on the y-axis, you can see some sort of normalized measurement of this amplitude of the XYZ. Now, typically, when we try to think of the data in that sense, the first thing we try to do is project it into a single vector. And this is known in this kind of field as the acceleration summary measure. So you bring the data from a three-dimensional space onto a single-dimensional space. And the first thing that, of course, most of you would think about quite rightly is you can apply the Euclidean distance. And that is a very legitimate way to do it. There are other ways to do it that we'll discuss in a bit. What you see with green is something we're going to discuss later. It's basically the automatically extracted slip. So I know that this audience would thrive and really want to see some equations. So here you are. So the Euclidean norm is what clearly all of you will recognize. The -1 is because we measure things in g, in units of gravity. So by default, if someone is not moving at all, the gravity is 1. So that is why we remove 1 to indicate that the Euclidean norm -1 basically would return a 0. Now, because of thermal noise in electronics, this might actually indicate a value which is slightly below 0. So that is why this Euclidean norm -1 has to be further bounded that you have non-negative values. And that is where you have this non-zero. And that is why this technique is called Euclidean norm -1 non-zero. So basically bounded that all values are non-negative. So that is the standard state-of-the-art technique that is widely used across your smartphones, your smartwatches, any of you that is thinking of having a Fitbit or your iPhones, your Android phones. Basically, that is the method that is used to summarize the three-dimensional acceleration data onto a single vector, and then they do some further processing. I was thinking about this a few years ago, and I was thinking that this whole formation, this simple equation, seems a bit artificial to me. So, of course, I can understand the concept of removing 1 to remove the gravitational effect, but this concept of ensuring that the data is non-zero in this way seems quite artificial to me. And then I was looking at the literature, what other colleagues have done, and there have been a few other attempts like this minimum amplitude deviation, which essentially extends the concept of what we have the Euclidean distance. There is this AI kind of concept where they try to look at the different axes, and they have something which is a bit more convoluted. And I was thinking that all of these are either a bit artificial to my taste, or they seem to be excessively convoluted. So then I tried to go back and rethink of the concept of why are we doing all that? And the reason we're doing all that is because we feel that there is this thermal noise which might perturb the data. So what I proposed was, let's think about getting the derivative of the data. So let's look at each of the individual axes. So there's the x-axis, the y-axis, and the z-axis. And let's try to take the derivative of each of the axes and effectively apply there the Euclidean distance. Now, what that buys us is that effectively we avoid the problems with thermal noise. And the reason is that if you have thermal noise, so this fluctuation that you might have some values that potentially go below zero when something is not moving at all, if you keep your hand still or if you put your watch standing on the desk, the thermal noise would come in bumps. So if you work on sufficiently small intervals, this will overcome this effect. So it is a very simple concept if you think about it, and it was the first concept I tried when I was looking at the equations that were established, and it's quite remarkable how well this works, as I'm going to show you next in next few slides. Just look at the equations, how they are, how complicated, for example, some that was considered maybe improves on the state of the art, and how my algorithm is. It is really, really simple and almost painfully accurate, as you're going to see in a bit. Some background before we get to see how we can assess this. So there are different activity categories. If you focus on talking with some colleagues that work in physical activity, they'll tell you that we have 4 types of physical activity. So we have sleep, which is the first type, and then we have the actual activity types, which basically indicate if someone is in a sedentary activity, which is pretty much like what you are doing currently. You're just sitting, hopefully intensively listening to what I'm presenting. There is a light activity, which is perhaps when you start walking, going for a coffee. There is the moderate activity, which is engaging in a bit of more aerobic exercise. And there is the vigorous activity, which you might think of when you go out for a fairly intensive run. So these are the 4 types of activity, and it's quite useful to try to think of ways that we can try to replicate these types of activity by using data we can collect from either the smartwatch or the smartphone. So what I've tried to do is explore the 3 widely used kind of approaches, along with my new acceleration summary approach, this ROCAM I've introduced, and try to see how things differ. And I've tried to do this with the default sample rate. So by definition, most of the studies tend to use 100 Hertz when they sample the data. And again, this was something that I kind of rebelled, because by Nyquist, we know that in practice, most of us will not be moving our hands more than 3-4 times a second, at which point it is becoming really excessive to be collecting data beyond 10 Hertz. As of course you know about the Nyquist theorem, we should be sampling with something with twice the sampling frequency of what the maximum frequency of interest is. So if we believe that most of us will not be moving our hands more than 4 or 5 times a second, then 10 Hertz should be fully sufficient. And what I've done is I've tried to see what happens with the state of the art, the established Euclidean norm minus 1 non-zero, and try to look at the different sample rates. So at 100 Hertz, and try to see basically, can I go down to 10 Hertz? Does it buy me something useful? Can I still do the analysis to be fairly meaningful? And you'll see that the correlation is, of course, as you might expect, fairly strong. But then quite interestingly, when you move with the other more complicated metrics, things get better. And what I would try to argue is that my technique might become the new standard, because just by applying a simple concept and considering the physical properties of what's happening, why we have the problem with the thermal noise, this kind of concept with using the derivative of the acceleration in every single axis and then applying basically Euclidean norm buys us all this great accuracy. And the even better thing here is that we can do this extremely well even down at 10 Hertz. Now, when I saw this first finding at the first time I've tried it, was, can it really be possible that my outcomes, my classical correlations are basically higher when I have a lower sample rate compared to a higher sample rate? It almost seems counterintuitive. But hear me out, I have a very good argument for that. The problem is that if you have very high sample rates, like 100 Hertz, then these spikes you might have might actually trip you off. So if you reduce that down to 10 Hertz, you avoid the problems with this thermal noise. And this concept of derivative basically overcomes the spikes that you might have, just precisely because you do not take into account the full high rate that you have in your data. So this is classical correlations, and I've done the full ML approach then by feeding both with thresholds and with more advanced methods, and I have verified that basically this new acceleration summary measure outperforms the existing acceleration summary measures in the literature. And just to give you an example here, when you try to use the established acceleration summary measures and my acceleration summary measure, just using classical thresholds, nothing too complicated, just a proof of concept, you can get a far better accuracy with the new acceleration summary algorithm. And this is some work I published last year. Now things get even better when you try to assess how well this assesses sleep. Remember, it's a fairly simple concept, what we try to do. And what we try to establish here is, can we correctly assess the onset and offset of sleep? Now, if you use your favorite Fitbits and so on, I can tell you that in many cases, many of these devices might miss completely the ground truth by many minutes. Probably the most established algorithm in the research literature currently is by Van Hees, that was published in 2015. And in fact, even this algorithm, which is better than many of the commercial algorithms, can miss things by quite a wide margin, particularly if you think about participants that have quite unique sleep problems. The other thing you should be aware is that many of these algorithms have been validated on healthy controls. They have not been extensively validated on people with sleep disorders. And that is another gap that I was trying to fill in my work. So I was trying to focus on people with post-traumatic stress disorder. So these are, in my case, primarily women that were raped or soldiers coming back from a war that have experienced traumatic events. And you can see that the state-of-the-art algorithms can miss the actual onset when someone starts sleeping and the offset when someone wakes up by quite a large margin, versus my algorithm that actually does far, far better. So the thing that is quite compelling then is that we can actually use the information we extract from the smartwatches, and you can see what we present, we call the actogram. So the actogram is defined as a 48-hour day. So you can see this is the Friday, 4th of July until midway. And then I hope you can actually see my cursor. Can someone confirm for me that you can see my cursor?
Yes, we can.
Brilliant. So what you see here is the Friday, 4th July, and then just following that is this Saturday, 5th July, which is exactly replicated below. So what you see on the second half of the graph is exactly replicated in the date below. And the reason we do that is because we try to visually appreciate what's happening around the midnight time. This is the classical way that circadian biologists are used to seeing the data, and we present the data in such a way to conform with the literature in this field. Now, the cool thing here is that, and the green here is probably say, is the automatically estimated sleep times. Now, the quite cool thing here is that just by wearing the smartwatch and doing the processing we have done, we can very accurately understand when someone is in different kind of sleep periods, and I've demonstrated before that we can do it far more accurately than the literature. The established algorithms in the literature. We can identify when someone is not wearing the device, which is this light brown color here. And we can see when someone has an activity during the night. So for example, this is probably time that someone went to the loo or to the kitchen to have a late night snack. So all these are characteristics we can try to use and characterize someone's sleep. Now, the interesting thing then is that we can actually use this information we can extract from the wearable sensors and map it onto characteristics that people might have. For example, people who have been diagnosed with bipolar disorders. You can use this information to understand if someone is in what we call manic phases, which is characterized by this light red color, or in depression phases, which is with this blue color over here. And that is quite remarkable because you can use the watch, it can get data for about 60 days on a single charge, and you can automatically assess if someone is on some of those psychiatric episodes. And of course, if you can do that remotely, you can try to inform someone's carers or someone's general practitioner to try to intervene early before something happens. As you might know, people with psychiatric disorders might be prone to, for example, suicide, or might be prone to other kind of disruptive behavior. And then we push things even further. So we have tried to establish if we can actually determine what happens before and after some kind of intervention. So people who have been diagnosed with, in this particular case, with post-traumatic stress disorder, they are prescribed a specific kind of psychiatric treatment. And hitherto, there is no established way, apart from hearing an expert psychiatrist, establishing whether this therapy has an improved effect on a participant. So as you can imagine, of course, many insurance companies are not really willing to pay money if they have to rely just on an expert's opinion. So for the first time, we can actually determine how things work objectively. And you can see here, someone before having the treatment has had much more disrupted sleep, in the sense that sleep was much more varying in terms of the onset and offset, versus after having the treatment. So after having the treatment, someone was behaving far better, they were sleeping more, they were having much more regular patterns, and that is reflected on the patterns we have extracted. The next thing we've done is we can try to actually also assess differential kind of treatment, and that's in stroke, that's in a completely different condition. So once again, by processing the data we have from smartwatches, we can establish very accurately which type of treatment might be preferential for different individuals. And everything is done completely passively. Someone just has to wear the watch, and we can follow them long-term remotely while they go at home. So patients do not really have to stay in the clinic any further. So this has all started from this algorithm that I've mentioned previously. Of course, we have done further analytics and further algorithmic development that I didn't have time to explain. For example, all these kind of characteristics that we use to assess the kind of different kind of activity that participants exhibit. And more recently, this is actually something that was published about 1 or 2 months ago. We have been doing this more holistically for endometriosis. Now, this is a condition that affects about 10% of women of reproductive age. So that is really something that affects a lot of women. And what we try to establish here is techniques that we can summarize information both from what participants can self-report and what we can extract from different sensors in terms of smartphones, smartwatches, and other characteristics we can assess in terms of their sleep, physical activity, and circadian variability, and provide some insights into the kind of optimized treatment that those women should have in order to lead a more normal life. And we can push things even further. So another study we've done with colleagues from Harvard 2 years ago, all we've done was using the acceleration that comes out of the smartphone. In that case, it was all participants with iPhones. And what we demonstrated is that just by having someone's passively collect data, just have your phone as you would normally do in your pocket, you can very accurately establish someone's cardiorespiratory function. So we've done it almost as accurately, or it was, I think, almost 88% accuracy, as someone would have to go into the clinic and be physically examined in the stress test and all this kind of treadmill assessments and so on. So all we would have to do is have someone use the phone. We will have access on the raw acceleration data. We can process the data and get something extremely accurate in terms of the cardiorespiratory condition, with, again, immense implications this might have in terms of informing their healthcare providers about what should be happening to monitor them early before they actually reach the stage that they got into the clinic. So far, I've tried to provide you with a thematic area of how things can work with processing actigraphy data from the smartphone and smartwatches, and try to develop some algorithms which are fairly simple, but are very predictive across a range of different conditions. I would like to turn the page and move on another area that I'm quite fascinated about, which is on information fusion. So the idea is that you might have a lot of experts, and each of those experts bring and complete a piece of the puzzle. Or sometimes you might want to have some of them silenced for a bit and basically try to weigh their input in terms of certain assessments. And again, this is something that you can probably all associate with. If you have a condition and you go into a clinician and they tell you that you have to take this drug or you have to go undergo some serious surgery, in practice, probably you wouldn't go with the first opinion. Probably you would go with the second opinion. And if those opinions are completely different, probably you go for the third opinion and the fourth opinion. And somehow then you think about how you can combine all these expert opinions that they have told you and come with the best outcome for you personally. How can you combine what people have said, their expertise, the background understanding of what you have, and actually come with a solution? That is exactly the setting we have here, and we try to formulate it using mathematical algorithms. So the way I was inspired and I came into this field was by processing voice data. And you may or may not be aware of, but actually just processing even a sustained vowel, someone saying ah, something that you might consider quite trivial, there are more than 100 algorithms in the literature. Now, that to me indicates that this is a far more complicated problem than just applying a Fourier transform or some other kind of single approach that would give me the fundamental frequency and we're all on the go and everything is sorted. So having more than 100 algorithms indicates that actually this is a problem that merits a further investigation. And when I started looking into the algorithms in more detail, I've started to identify that all of them had shortcomings. So then I had an idea. Then I thought, what if I can view this problem like the case where I explained before, that you have a problem and you get the opinion of different experts. I'm thinking about something about my cardiovascular condition. I talk to the first cardiologist, then I talk to the second cardiologist, and so on. So this cardiologist in that case could be the F-naught algorithm. So how can we try to combine all these experts? In the first case might be humans, in this case could be algorithms, in another case could be sensors. So how can we combine all these collectively known as sources to identify something that is far better? Now, one setting that, as I said before, that is quite commonly used in the clinical practice is that you might have multiple experts, and quite frequently there is no ground truth. And with apologies to if you have any clinicians in the room, usually the ground truth is established by the most senior person in the room. If you find yourselves in the medical school like I find myself, the ground truth is usually the senior person in the room. That's the established and what is believed to be the truth. Now, in practice, you might try to argue that if you were to combine experts, potentially in a time-adaptive way, you might get a best estimate of the ground truth. And that can be quite tricky in practice if you do not have any way to actually measure the ground truth. But thankfully, in our example here, we have ways that you can actually measure the ground truth that we'll be using, and then we can extrapolate into other problems as well. So some equations again to keep you on your toes and happy about how things are expressed mathematically. If you try to think that you have collected some data, you have some samples that you are recording, so you might think that this is me, this is Paula or someone else. So you have a few participants, let's call them N participants, and you can have a different kind of algorithms, or as I said, generally you can think of them as sources. So they provide an estimate and another estimate and so on. So you can have M estimates from the M different sources. Now that gives you an overall estimate, if you will, by having some way to combine them or having some way to identify which one of the experts you believe, and you have some sort of ground truth. So the concept here is, of course, you want to minimize some loss function that your estimate is as close as possible to the ground truth. So it's a fairly easy, intuitive idea that you want to find some functional form that you will combine the underlying experts or sources that will give rise to some sort of estimate that is ideally as close as possible to the ground truth. Now, there are different ways that you can try to impose this kind of concept of information fusion. And I remember the exact date. It was Christmas of 2012, the Christmas day. Instead of having a day off, I was actually reading this paper. It was published by some colleagues from Harvard. So what they were putting forward, they were saying that they were going to use the Kalman filter. All fine. I was taught about the Kalman filter in my undergrad. So the concept is basically you can think that the current state that you have is a linear function of the previous state, so all fine, plus some input, which again can be affected by what can be affecting this state, plus some noise. And then you have to take into account that this actual state that you're computing is actually a measurement of the state, is not the true state. Just to put things in perspective, if you were to think of measuring my heart rate, the best way to do it is actually open my chest and look directly at my heart, right? That's the best way you can really get a sense of how fast my heart beats. Instead, that's very a very extreme example, but hopefully will drive home the point. The idea is that what you are measuring is, we believe, a linear function of the true state. So what you're measuring externally, putting like a stethoscope or some external device, is measuring what we think is a linear function of my underlying true state of how fast my heart beats without actually going and seeing it firsthand, plus some noise. Now, when I was reading that paper by Harvard, as I mentioned, I was looking at the way that they were trying to set up the covariance matrices, because when you think about the Kalman filter, the key problem that you have is how these covariance matrices are going to be set up. So we presume that the noise is Gaussian, so we presume that we have a classical linear form of the Kalman filter. And the key problem here is that even if we presume that the noise is zero, which seems a reasonable assumption, like in further information, how are you going to set up the covariance matrices to actually move things forward? And the way they've done it is that they said, we're going to work at its source separately, and going to presume that the Q, which I'll remind you is the state noise, they presume that that is constant. And I remember that Christmas Day, I'm reading about this paper, I'm thinking, well, is it really constant? Can we say that a single expert has constant noise across every single patient? It just seemed, again, very artificial to me. I couldn't believe that a sensor or an algorithm could be exactly the same wrong or right with every different signal. It's exactly the same case with a clinician. That clinician cannot be exactly the same right or wrong for every single individual they see. So in other words, setting up this covariance matrix to be constant by colleagues, Lee was in Harvard at the time and Amati was in MIT at the time, to me it seemed quite restrictive and too much of a simplifying assumption. So what they were doing was that they were only adapting the second covariance matrix. And on the basis of doing that, they were introducing signal quality indices. But again, the way they were doing it, it felt to me that it was done externally to having the full formulation. I could see why they were doing it, because they want to work with a vector, and vector algebra is, of course, much simpler compared to matrix algebra. But still, it felt completely artificial. Why you invoke the Kalman filter as an information fusion approach, you do things externally, you set up something simply to be constant, which we know in practice would definitely not be the case. The whole thing seemed to be quite artificial. So as I tried to mention is that I was reading the paper and I was trying to identify all these problems, that the state noise simply is not always constant in practice. You cannot have the same error for every single patient. The interactions are not taken into account simply because they have the linearized, vectorized formulas. So effectively, how can we try to address these limitations of those two key papers? And by the way, one of them won the Martin Black Award paper in 2010, I believe. So how can we try to address this kind of shortcomings that they have? And then I try to think of, can we actually work slightly more rigorously using matrix algebra to work collectively with all the sensors at the same time, invoking the Kalman filter as an information fusion concept, but working collectively. And then the other thing, of course, I want to set up both the state and the measurement noise to be completely adaptive on the data. And in both cases, I want to adapt the covariance matrices completely adaptively on the basis of the data I'm collecting. And I'm trying to assess and have some prior beliefs about what each of the sources can have. And the data can tell me about how much I believe in each of those measurements. And the other key thing is I want to not to have this to be external, but also to be time adaptive. To me, that was the key thing, because with time series that I'm tend to working on, like with voice, or with any other time series that you might think of, like in the papers they published for example, assessing the photoplethysmography or heart rate, things tend to vary with time. It's not just a one-off that you have a clinician assessing you. These are algorithms that vary with time. So I want things to be done completely adaptively and to take into account the concept of time. So that's when I had this eureka kind of moment, that I can actually work with matrices instead of vectors. Now, the key concept there is that I can work directly with the covariance matrices, where I can specify that I tend to believe something is a value which is constant, provided that the underlying best experts are below a threshold. In other words, what I'm saying here is that I can believe what the previous paper said if the signal is not of sufficiently good quality. So this is the signal quality index. If the experts, you might think of the expert cardiologist 1 and the expert cardiologist 2, these are the two experts in the world. In this case, these are the two probably most successful algorithms for F-naught estimation in the context of voice assessment. So if these algorithms are very noisy, the signal quality index is not sufficiently good, then for lack of something better, I can believe that the noise that you have is something constant. Otherwise, if you have algorithms which are fairly confident in their assessments and the signal quality index is quite high, then I want to make this completely adaptive. And that completely adaptive is something I'm going to define on the basis of additional, what I call bonuses and penalties, which is completely application driven. Now, the concept then is that you're going to introduce some bonuses and some penalties, which effectively reflect how much belief you have in each source. And I remind you, by source, I refer to the algorithm or that expert. So that expert might be someone that I really believe or don't believe. Now, these are application dependent, but long story short, essentially what they say is that if you have this algorithm which completely deviates from its previous assessments or completely deviates from other robust assessments of, for example, the mean or the median of the other algorithm, so it has a complete difference from the best expert, then it has to be suppressed, and so on. That is quite application dependent, and that requires a lot of experimentation and some knowledge understanding of that particular domain. In terms of the actual application of the algorithms, you can see the mean absolute error. So when you apply some algorithms, for example, this Pratt is one of the state-of-the-art algorithms used in this field. It is actually quite way off. Some of the algorithms are doing far better. So it's only 3 hertz difference compared to what you have on ground truth. But the cool thing is that when you apply this information fusion algorithm, not only you improve the actual mean value, but you also minimize the problems with the uncertainty you have over the full estimate. And this might seem like a small improvement, but it's actually full 16-17% of improvement in terms of quantifying the F-naught assessment. And if you want to see it visually, anything that is below 0 indicates that the information fusion approach is far better for that unique signal. Anything that is above 0, it indicates that the single best expert outperforms this information fusion scheme. And I hope you can see my point that the information fusion scheme is far better. In fact, for those signals, it was way better than the single best expert. So that was a paper I was very happy when I published in 2014. So now let me move on an area that has been very dear to my heart since my PhD days. If you think about the classical perspective of analyzing data, you start with visualizing the data, exploring the data, applying some kind of statistics and visualization and correlation analysis and so on. The next part, when you get towards the ML approach, the first thing that you tend to do is feature selection or feature transformation before you actually get on the statistical mapping with applying your favorite classifier or regressor. Now, very broadly, to paint this picture, you start with the data that you have some sort of structured or in unstructured format. You extract the features of the data, and then you use that to map into the clinical outcome in my practice. So you can start with any kind of data. In my case, that's usually time series. So that's the electrocardiogram, how well my heart beats, and so on. Electroencephalogram, how fast brain signals propagate, activity, location, and so on. So you apply some signal processing algorithms, you can extract the characteristics, you can put into that design matrix format. And by the way, that entire formulation is fully adaptive. You could have here images or videos, and you would just adapt these algorithms over here to extract a design matrix that you can move on. Now, the problem in practice is that this might be really high dimensional, as you're going to see in the next slide. So you might have here a design matrix where you have your n samples, and this space, this m dimensional space, might be potentially thousands and thousands of features. In practice, usually you're given the outcome. Definitely in the clinical settings, you have something to work on that can be measured or provided. And the problem is, as of course you think of in most problems, is finding some compact way to extract the information content of the design matrix and map it onto the outcome. Now, before you rush to use all the features, it is useful to identify which of the features you want to use. It is conceptually not too dissimilar to what I presented before about information fusion, only that this time it's not time adaptive. It's one-off. You decide this feature is going to contribute, this feature is going to be completely discarded. The key thing that this is far better, for example, than a PCA or some other feature transformation technique is that you retain interpretability of that domain. So by retaining feature number 5, you retain this understanding of what clinicians have about what this feature number 5 indicates in that domain. And in practice, if you have, for example, microarray data, that is really what you should be doing. You can think of a case by microarray. I think of problems like where you have multiple genes. You might have, for example, 10,000 genes. It would not really make sense to apply PCA and tell to a biologist or a clinician that it's a little bit of gene 3 and a little bit of gene 5 and a little bit of gene 100, and that predicts cancer. Ideally, what you want to tell them is that look at gene number 3, look at gene number 5, all those 2, 3, 4, 5, whatever genes, these are predictive of cancer. So it is really a useful setting to think of how we can identify which of those features can actually be used in the subsequent phase of statistical mapping. Now, there are 3 concepts I need to introduce you before we get on the algorithmic development. So the first one is what we call the relevance. Essentially, what that means is that you try to extract how much a feature is associated with the outcome. And if I were to ask you, for example, that you have this feature X and feature Z, and you try to see how much they contribute in terms of Y, maybe we'll agree that feature X have some more explanation in terms of the Y than Z, give or take. So in that case, you would prefer X, or you might say, okay, in this case, they're probably about equal. So in that case, both should be selected. You can see the concept, how much each of the feature univariately corresponds to explain the information you have in the outcome. The second concept is the concept of redundancy. So ideally, you want the features you will select not to be having too much overlapping information, because otherwise they're basically redundant. They're not offering something useful over and above what the prior feature has offered. And the third concept that is frequently not really used in practice is the concept of complementarity. So how can you combine features together? And this combination actually is more than the sum of the parts. And the way I'm explaining this to my master students is if you're aware of, for example, Boolean algebra. Oh, apologies for that. If you think about Boolean algebra, it is quite important to consider things in terms of pairs. If you think the XOR, for example, just using the X1 is not predictive of Y, it's about 0.5. The X2 on its own is predictive of Y with about 0.5 correlation. You have to take both X1 and X2 to be really predictive of Y. It is the same concept in biology. A single mutation of a single gene does not cause cancer or some other kind of disorder. Again, a second gene on its own, if it's mutated, it does not cause cancer. A third gene on its own, if it's mutated, does not cause cancer. If all 3 are mutated, they cause cancer. So how can we express that mathematically, that combination of different variables expressing to try to identify this information? As you might imagine, there are probably hundreds of algorithms for feature selection. One of the most commonly used algorithms is called MRMR. And the reason I've used that is because I really like the concept that it relies firmly on the concepts. It uses relevance and redundancy, and effectively what it tries to do is it maximizes this product. It tries to maximize the relevance of a feature and minimize the redundancy of a feature on the extracted feature subset. That is the entire concept without going into too much detail. And in practice, has worked remarkably well. If we have colleagues from a statistical background in the audience, they would probably immediately think of the L1 penalization, lasso, and so on. And that is another technique I've tried. So there are lots of different ways that you can try to identify which features might be predictive of an outcome. So I was trying to think of that problem, and I was banging my head on the wall with existing approaches, and things were not working for me for a long time. So I think I was working on that problem for about 6 months. And then one evening I decided that I've had enough. I'm going to watch this movie, A Beautiful Mind. So as I was watching that movie, and you recognize here Russell Crowe, he just said this thing at some point in the movie: the best result will come when everyone in the group is doing the best for himself and the group. And that actually statement gave John Nash, the scientist that Russell Crowe impersonates, the Nobel Prize. And I remember that's a true story. I remember when hearing this line that I paused the movie, I went back into MATLAB and I programmed the whole thing. So that line for me was the inspiration for actually developing this algorithm. So essentially what I've done is I'm trying to look into the relevance, like the MRMR algorithm, the redundancy, like the MRMR algorithm, and that part, the complementarity. And I know that this sounds quite complicated. I'll try to explain to you briefly. That all came just by hearing this sentence. And somehow subconsciously thinking about the literature I was reading in my head. And basically, this additional term gives rise to what I call this relevance, redundancy, complementarity trade-off. So this RRCT is a new algorithm I developed. And I'm going to show you that generally it tends to work remarkably well. So very briefly, what it tries to do is it tries to transform the original correlations. You have, again, some matrix algebra. The great thing here is that if you have very low correlations, basically, this goes zero. If you have fairly high correlations, the magnitude of the correlations, basically, you do not really care. If something has a correlation coefficient of about 0.8 or something, you don't really care. What you really care is about this mid-range, so something between 0.3 and 0.6, 0.7. And that is actually seen to map very well with this kind of information theoretic concept transformation. And then the next part is about assessing this concept of how you can bring things together. And again, you can invoke concepts from linear algebra with partial correlation coefficients to account for conditional probability. So essentially, it's a concept where you identify the association strength between variables conditioned upon some external variable. You can do that very efficiently with partial correlations. Now, there are two ways to really assess how well things work in practice: using synthetic data or real-world data to assess if a feature selection algorithm works well. In my case, I've tried with 12 datasets. So what you can see on the y-axis is the false discovery rate. Ideally, this will be 0. And what I've tried to do is I've tested out 19 state-of-the-art algorithms plus mine, RRCT, 20 algorithms. So I have 20 algorithms across 12 datasets. And these are some of the tricky synthetic datasets. You can see that my algorithm is exactly stuck on 0 with the exception of this dataset where I make one mistake at the very final run. So ideally, you want things to be completely 0. You can see some of the state-of-the-art algorithms are basically getting it 100% of the times wrong. That means that every single feature they've selected is not the right feature they should have been selecting in the first place. And that's quite remarkable. So these are particularly tricky synthetic data sets. And when I tried my algorithm, it was working very well on this kind of synthetic data. I was feeling quite optimistic. And then I've tried, of course, with some real-world data, and things in general were working very well. So you can set my algorithm. Here it is, RRCT. In this particular case, completely outperforms some of the state-of-the-art algorithms. So it's misclassification. The lower you are, the better. You can see some algorithms that have been very widely used, like this hit-on has been popular in some contexts. It basically fares quite badly. Now, I will not be a person that will suggest my algorithm is the best thing since sliced bread. There are some cases that, for example, in this case with only 4 features, this particular algorithm, DASR, is performing better than my algorithm. But overall, you can see that if you are happy to go with 20 features for this dataset, again, my algorithm goes far, far better. And there are some datasets indeed that my algorithm was not the best performing algorithm, but the good thing was that it was probably the second best or the third best. So it was very near the top. Like you can see here, for example. So this particular dataset has a different algorithm, this LSMI, that is overall better, but overall you can see my algorithm is probably second best. And again, in our dataset. So overall, that means that we can be fairly confident that this new algorithm that is based on fundamental key principles is very robust. And the good thing is that in terms of how much it takes to run, it is fairly in the mid stage of comparing with other algorithms. So overall, it probably takes about a few seconds or maybe a minute to run on a very large data set. So it can scale very well. This algorithm has been highlighted, for example, by the Turing Institute. You're very welcome to look at this blog where we explain how this can work more broadly. It's something versatile. It can work across any domain where you have data can be presented in the form of a design matrix, and you try to identify a robust feature subset. I'll try to wrap up and mention that a lot of these concepts I've mentioned and have coded in most of the cases. They're in MATLAB code. You can find all the data and code in our website. If you remember nothing else from my talk today, you can remember the name of my group. No prize given for my preference in terms of movies. We're called the DART group because I'm a big fan of Star Wars. So if you're interested, this stands for Data Analytics, Research and Technology in Healthcare. So if you search for DART group, you'll find all the code and the data we have been using in all the papers that underline my talk today. I'll try to summarize in the last minute or so, and then I'm open for questions. That I think all these new technologies, the smartphones, smartwatches, all this big data that we come to face these days provide us with unprecedented opportunities. I'm really grateful I live in this era and I have this technology and this use of tools and mathematics and programming to actually test out solutions and develop something useful. And the other key thing that I think hopefully stands out from this talk is that it frequently pays to go back and revisit the fundamental concepts, and building on those concepts and understanding the problems, we can develop simple and yet really powerful algorithmic expressions and algorithmic solutions that work in practice. If we do all that, I think we will be getting closer to delivering what Barack Obama has been talking about, that we are the change we have been waiting for. We are the people that will really change the world for the better. Thank you very much. I'm very open for questions.
Thank you very much, Thanasis. Any question? I have one question for you, Thanasis. It's more a personal opinion. There is this huge amount of data on one side with these powerful algorithms, and on the other side, there are the physicians who are still reluctant to use this data. I see a big gap between the medical world and this huge amount of data. Do you think that this will be changing in the near future?
Yeah, so the quick answer is yes. And I think currently part of the problem is that many of us mathematicians, engineers, we used to be working in silos. So prior to coming to Edinburgh myself, I used to be based in the mathematical department. And being in the mathematical department, sometimes it takes a lot of effort and time to build the trust with the clinicians, to give you the data, because of all these ethical implications, these worries that they might have of what might happen if something goes wrong. So I think one way to do it, and that's not the only way, but one way to do it is what people in Edinburgh have done. So they try to recruit people like myself, coming from an engineering background. We have colleagues from computer science, coming and being embedded into the medical school. And just this proximity, this day-to-day interaction with clinicians is actually quite useful to earn their trust and actually accessing the data, develop something that they would want to use. If nothing else, having me around the corner every day and telling them about something useful in terms of data analytics will probably encourage some of the clinicians to potentially use something. Whereas I think in the past, when I was in the mathematical department, I might be shouting at the top of my lungs, but they would not hear me at the medical school. So that is one way that this may be working. But I think this is probably also a cultural change that is progressively happening. So we see in the UK, we have this UK Biobank. In the States, there is the PhysioNet. There are all these big efforts where clinicians, I think, increasingly understand the power of the data, and they use that people like us, coming from a non-clinical background, we have the technical expertise, we do not have the clinical expertise, but I think they understand how we can try to work together to really solve some of the key challenges. The key problem is that sometimes they do not really see the value. They're worried that we might be adding burden in what they add. So if we can develop something that we can convince them that we try to save on resources, save on effort, actually make their life easier, I think that's something that we all have to gain.
Okay, maybe explainable artificial intelligence can help in that sense. Okay, thank you very much.